Exchangeability of continuous random variables is a lot like exchangeability of discrete random variables. The only difference is we talk about random variables being less than or equal to a value instead of being equal to a value. So given continuous random variables, x1 through xn, we call them exchangeable if for all vectors a1 through an of real numbers and all rearrangements b1 through bn of a1 through an, we have that the probability that x1 is less than or equal to a1 through xn being less than or equal to an equals the probability of x1 being less than or equal to b1 through xn being less than or equal to bn. In other words, the joint cumulative distribution functions satisfy f of a1 through an equal f b1 through bn. Or equivalently, the joint probability density functions satisfy f a1 through an equals f b1 through bn. So one way of recognizing that random variables, continuous random variables, are exchangeable is to see that the joint cumulative distribution function f of x1 through xn, or the joint probability density function little f of x1 through xn, is a symmetric function of x1 through xn. Symmetric function means that if we swap any variable for any other variable, the function doesn't change. So for example, let's look at symmetric functions of three variables. So functions like x1 plus x2 plus x3 don't change if we swap out any one variable for any other. We make this x2 plus x1 plus x3, that's exactly the same. Similarly, x1 squared plus x2 squared plus x3 squared is symmetric. x1 x2 plus x1 x3 plus x2 x3 is symmetric. You can see that if we swap out, if we change all the x1s to x2s and all the x2s to x1s, this becomes x2 x1, which is the same. This becomes x2 x3, that becomes x1 x3. So it doesn't change if you swap any two variables. You could swap 2 and 3, you could swap x1 and 3. and some other symmetric functions in 3 variables. We could add the cubes of all the variables. We could take the product of all 3 variables. That's the same if we swap 2 variables. We could take the sum of all products of one variable squared and another variable. So x1 squared x3 plus x1 x3 squared plus x2 squared x3 plus x2 x3 squared. You can see that all the variables enter into this formula in exactly the same way. So if we were to swap all of the x1s with x2s, we would get the same function back. Alright, now let's look at a probability density function that is symmetric. So for example, let's let x and y be continuous random variables. With joint probability density function f of xy equals 6 minus 6x minus 6y, or 0. The first formula, if x plus y is less than or equal to 1, x and y are greater than or equal to 0, and 0 otherwise. So this is defined over the region in the xy plane. That's this triangle. This is the line x plus y equals 1. So we can see in this formula that if we were to swap all the x's and y's, the same thing, the formula would stay exactly the same. 6 minus 6y minus 6x is the same thing that we have. And the region wouldn't change either. If we change this to y plus x equals 1, that's the same thing as x plus y equals 1. X and y being greater than or equal to 0 is the same as y and x being greater than or equal to 0. Alright, now let's integrate this and get the joint cumulative distribution function and see that that's a symmetric function of x and y also. So, since the variables here, x and y, are the same as there, let me use dummy variables in here for integration purposes. So I'll write f of s and t, and I will integrate ds and dt. So we have, if s is going to be the variable that we're integrating to x, x is going to go from 0 to 1 minus y. I'm sorry, I've written this wrong. We really want to integrate s from negative infinity to x and t from negative infinity to y. It doesn't matter how high those things can go. So s is going to go from 0 to x, because for x less than 0 we just have 0 here, and t is going to go from 0 to y. And the function is 6 minus 6x minus 6y ds dt. And this is an S and this is a T. Because we're putting f of st in here. So we integrate ds and we get six s minus 6s squared over 2 minus 6ts, evaluated at s goes from 0 to x dt. When s equals 0, this whole thing is 0, so we end up with 6x minus 6x squared over 2 minus 6tx. Now we integrate this dy. So we have 6xy minus 3x squared y minus 6. Sorry, we're integrating this dt because t is the variable that's going to become y. 6xt minus 3x squared t minus 6t squared x over 2. Now as t goes from 0 to y, and this is 6xy minus 3x squared y minus 3y squared x, and then we plug in t equals 0, this whole thing is 0. So this is the cumulative density function. Capital F of xy equals 6xy minus 3x squared y minus 3xy squared. So we can see that this doesn't change if we swap x and y. 6xy is the same as 6yx. And if we change this to minus 3y squared x and this to minus 3yx squared, that's exactly what we have. We're just swapping these two monomials. So if we pick a point in here, say 1/3, 2/3, so this point, f of 1/3, 2/3 should be equal to f of 2/3, 1/3. F of 1/3, 2/3 equals 6 times 1/3 times 2/3 minus 3 times 1/9 times 2/3 minus 3 times 1/3 times 4/9. And f of 2/3, 1/3 is 6 times 2/3 times 1/3 minus 3 times 2/3 squared is 4/9 times 1/3 minus 3 times 2/3 times 1/9. So you can see these two terms are exactly the same. 6 times 1/3 times 2/3 minus 3 times 9, 3 times 1/9 times 2/3 is here and here. Minus 3 times 1/3 and 4/9 is here and here. So the function is exactly the same. Now, a consequence of exchangeability of continuous random variables is just like the same consequence we have for discrete random variables. That is, if continuous random variables are exchangeable, then they end up being identically distributed. So if continuous random variables x1 through xn are exchangeable, then they are identically distributed in the sense that the probability that x1 is less than or equal to some value c equals the probability that xi is less than or equal to that same value c for I equals 1 to n and any c. So to see this, let's just write out these two expressions according to the definition. So by definition, the probability that x1 is less than or equal to c is an integral actually it's n integrals. So let's write f of x t1 through tn minus 1 dt1 through dtn minus 1 through dt1 dx. So we'll put the dx integral first, and then the t1 is going to go from negative infinity to infinity, and tn minus 1 is going to go from negative infinity to infinity. So we're integrating out all of the variables t1 through tn minus 1, and then we're going to let x go from negative infinity to c to get the probability that x1 is less than or equal to c. And then if we write the probability that xi is less than or equal to c, now we can do these integrals in any order we want and get the same answer. So I'm going to let's look at the function f of t1 through ti minus 1. Then I'm going to put x in the ith place to represent the variable capital Xi, and then ti plus 1 through tn minus 1. And then the same dtn minus 1 through dt1 dx. When we take the integrals, oops, this one should be tn minus 1. And we're starting with t1. Well, starting with tn minus 1, working up to t1. So again, getting rid of all the variables t1 through tn minus 1, which we can do in any order, and then letting x go from negative infinity to c, so that the probability that xi is less than or equal to c is what we're computing. Alright, so those are just expressions for these probabilities by the definition of how we use the density function to get these probabilities. But by exchangeability, of x1 through xn, these two density functions are exactly the same, because they differ only by swapping variables, and we're allowed to swap variables for exchangeable functions and not get anything different. So then if we do these integrals in this order, saving x1 for last here and xi for last here, then we get the same integral. Alright, so since continuous exchangeable random variables are identically distributed, it's natural to ask, are continuous identically distributed random variables necessarily exchangeable? And the answer is no, they're not. And we can show this with a simple example. Let's consider three random variables, x1, x2, and x3. With x1 uniform on the interval from 0 to 1, and x2 and x3 both equal to 1 minus x1. So that means that x2 and x3 end up being uniform on 0, 1 also. So these are identically distributed. So if we look at the probability that 1 is less than or equal to, x1 is less than or equal to 1, x2 is less than or equal to 1/3, and x3 is less than or equal to 1/3. These are exactly 1 minus whatever x1 is. So this is just the probability that x1 is greater than or equal to 2/3, because these are less than or equal to 1/3 precisely when x1 is greater than or equal to 2/3, which is 1/3. But if we permute the numbers 1, 1/3, 1/3, and look at the rearrangement, 1/3, 1, 1/3, and this probability is 0. Because x3 being 1 minus x1 means that x1 plus x3 is always equal to 1. But if x1 is less than or equal to 1/3 and x3 is less than or equal to 1/3, then they can't possibly add up to be 1. So that means that x1, x2, and x3 are not exchangeable. So just like in the discrete case, if we have exchangeable variables, they're necessarily identically distributed, but if we have identically distributed random variables, they're not necessarily exchangeable. The end.